I want to talk about a mostly complete version of the quantum hydrogen atom. It leaves out the effects of relativity, but it recovers most of the features of the Bohr model, the ones that he got correct, but also gives us some other sort of new and interesting results when we take a look at quantizing the rotational portion of the electron's orbits. So, to treat the hydrogen atom more properly, we would need to apply the Schrodinger equation. And for the radial part of the Schrodinger equation, we would have similar form for the one-dimensional square well, minus h bar squared over 2m. We take the second derivative of our wave function, and then we would have to add our potential energy times our wave function. So for the case of the hydrogen atom, it would be minus k times the electrical charge squared divided by the radius times our wave function's radial piece, and that would equal our eigenvalues, our quantized energy levels, E sub n, times our wave function. And it's important to note here that the radial coordinates and the angular coordinates describing the wave function for those electrons are totally separable. Just like time is separable from space in most of the quantum applications we're talking about, what we call time-independent wave functions. Well, when we solve this, it involves series of functions that all have a dependence on e to the minus the radius divided by a series of constants that are exactly the same as the Bohr radius A0, and the eigenvalues that we get would be energy levels of minus Coulomb's constant times the charge squared divided by 2 times that Bohr radius times 1 over n squared. It's the exact same energy levels that Bohr worked out, but it's from the governing equation of non-relativistic quantum mechanics in the radial direction, not using an argument of circular orbits and quantized angular momentum. Now, speaking of angular momentum, the angular momentum comes from the allowed orbits. And when you end up quantizing the radial components end up creating what are called spherical harmonics. And in terms of quantum numbers, we need a total of 3 quantum numbers. And that's going to be true for any quantum system. For every dimension in which the system is quantized, you get a quantum number. So if you were to look at a 3-dimensional square well, you would have an n in the x direction, an n in the y direction, and an n in the z direction. With radially symmetric functions, we would have a radial quantum number, and our radial quantum number is n, the energy level of that particular orbit. So all orbits within the same value of n have approximately the same energy and would have the same energy under this sort of first principles look at quantum mechanics. Now, in angular quantization, our 2 angular variables would be an angle theta and an angle phi, where phi is down from what we would sort of think of on the z-axis, and theta is a rotation around that axis. So in terms of quantum numbers, we call our 2 quantum numbers L and m sub L. Now what L is doing, L is the orbital quantum number, and it's the number that allows us to quantize angular momentum. And there's some restrictions on L. N can be any integer from 1 to infinity. L starts at 0, and there are angular momentum states from 0 all the way up to n minus 1. So that's a big break from the Bohr model right there, because Bohr assumed angular momentum and energy were pretty much co-quantized. They were one and the same. So for the n equals 1 level, we only have one value for L, 0. But at n equals 2, we could have L equals 0 or L equals 1. At n equals 10, we could have any value for L from 0 all the way up through 9. Now the last quantum number is called the orbital magnetic quantum number, and what it does is it quantizes the projection of angular momentum along the axis of the magnetic field, because when you apply a magnetic field to a quantum electron orbit, the angular momentum ends up precessing around the axis of the magnetic field. So, I'll get into the math of that in just a second, but to talk about the limits on the orbital magnetic quantum number, m sub L can take on any value from negative L all the way up through L in integer increments. So, for the case of L equals 0, the only value we get for m sub L would be 0. So at the n equals 1 energy level, there's one set of numbers we can use. N equals 1, L equals 0, m sub L equals 0. At the n equals 2 energy level, well, it's still valid to have L equals 0 at n equals 2, so we would have a 2, 0, 0, and then we would end up getting 3 orbits with an L quantum number of 1. So we could have 2, 1, plus 1, we could have 2, 1, 0, and we could have 2, 1, minus 1. All 3 of those are all unique orbits. And the way that those orbits would work, for the orbit plus 1, if this is the axis of my magnetic field, my angular momentum would have a precession around that magnetic field axis. The amount of angular momentum along the axis of my magnetic field is my m quantum number times Planck's constant h bar. And the amount of angular momentum in each one of those states is going to be the square root of my L quantum number times L plus 1, all of that multiplied by the Planck constant over 2 pi h bar. Now, this is another big departure from the Bohr model, because the Bohr model assumes that the lowest amount of quantized angular momentum would be h bar. The lowest amount of quantized angular momentum is 0. If L equals 0, little l is 0, there's 0 angular momentum. Now if L equals 1, the amount of angular momentum isn't 1 times h bar, it isn't 2 times h bar, it's the square root of 2 times h bar. If L equals 2, we get 2 times 3 under our square root, it's the square root of 6 times h bar. We're not getting integers for the amount of angular momentum. Now if we start making these quantum numbers huge, the difference between L squared and L squared plus L is negligible, so then we would start seeing quantum angular momenta that wouldn't look like they're going like an integer times h bar. But until we start getting to huge L, we have to make use of this quantum scheme. Square root of an integer times the next integer times Planck's constant over 2 pi gives us our angular momentum. So, if we were to say have h bar projected on the z-axis, which is the axis we use for the magnetic field by default, we just say it's the magnetic field in the z direction. For the m equals 0, it would just be spinning in the xy plane for the precession of the angular momentum. And for ml equals a negative 1, we would be on the negative z-axis a value of h bar. So we could figure out the angle between the magnetic field and the axis of the angular momentum. The cosine of that angle from the axis of the magnetic field would be the amount of angular momentum along the z-axis divided by the total angular momentum. So since they're both dependent on h bar, the cosine of that angle of the precession of the magnetic field axis to the axis of the, or precession of the angular momentum axis compared to the axis of the magnetic field, the cosine of that angle is our m quantum number divided by the square root of the quantity L times L plus 1. Thanks for watching.